So in previous lecture we have finished with the various terms like specific conductance, molar conductance likewise. Now we will see the variation of this molar conductance with the concentration for the weak electrolyte and strong electrolyte. So what do you mean by first weak electrolyte and strong electrolyte? So the weak electrolyte is simply the electrolyte which is not completely dissociated at a given concentration, but for the strong electrolyte we can say that the strong electrolyte dissociates almost completely. Okay, so that is the difference between weak electrolyte and strong electrolyte. So like we basically say that salts like NaCl, KCl or HCl, likewise they are the strong electrolyte, and the acetic acid or some organic acids are weak acids or the weak electrolytes. So it is found experimentally that both the specific and molar conductance of a solution will depending upon the concentration, and the specific conductance is increases with increase in concentration, while this molar conductance decreases with increase in concentration, or we can say that this molar conductance increases with increase in dilution. So these are the two important parameters that we need to consider. That one is what, the specific conductance kappa increases with increase in concentration, whereas molar conductance lambda m increases with decrease in concentration. So this is an inverse relation, and we know that this is why, because formula for this lambda m is what, thousands of k upon c. Okay, so lambda m is inversely related with concentration, so it is decreases with increase in concentration, or it is increases with increase in the dilution. So the variation of the linear molar conductance with the concentration is different for the strong electrolyte and weak electrolyte. So in the case of strong electrolyte, the number of ions per unit volume of a solution increases in proportion to the concentration. However, for the electrolyte, we know that for the weak electrolyte, the number of or the decrease in concentration will not resulted into the same amount of ions that we are expecting. So the increase is not cannot be so large because of the changing into the partial ionization of the solute, and hence consequently the conductance will not go rapidly as strong as the strong electrolyte. So this is the observation that we have obtained if we plot the graph of lambda m versus under root of c. So here we can see this is for the strong electrolyte, so it is showing the linear behavior, but for the weak electrolyte we cannot get the value of or the linear behavior for the weak electrolyte like acetic acid. So if you want to find out the molar conductance at infinite dilution, so just by simply extrapolating this graph on this molar conductance value, you can get the molar conductance at infinite dilution. But for the weak electrolyte, we cannot like extrapolate this graph, because this graph is tends to what, infinity. So due to this, the molar conductance at infinite dilution for the acetic acid cannot be determined directly by using the this extrapolation graph extrapolation method. So what we can do, so in order to like find out that, we will use the Collar's law. So we will see that. So here are the some observations that we have made for the various solutions like KCl, HCl or acetic acid. So here upon dilution we can see this, the molar conductance increases upon dilution. Okay, so Collage was the first one so as to observe that in the lambda for strong electrolyte is being plotted against the C, the straight line is obtained for the strong electrolyte. So he has proposed that the empirical equation for the strong electrolyte, that is lambda is equals to lambda m naught minus b into under root of C, where lambda is the molar conductance of a solution for the given concentration, which is expressed in the moles per dm cube or moles per liter, and lambda naught is what, the molar conductance at infinite dilution, or simply we can say that it is a zero concentration. So the straight line plot is only observed for the uh, strong electrolyte, so it is called as a limiting conductance for the strong electrolyte. So this is only applicable for what, strong electrolyte, and not for the weak electrolyte. So due to the non-linear variation of the molar conductance with concentration, the same method which cannot be used for the solution of weak electrolyte. So in order to find out this how that weak electrolyte is changes its conductance, SRNES has explained the increase in the molar conductance with the decrease in the concentration. So according to this theory, when the electrolyte is dissolved in the solvent or water, it will dissociate it into its constituent ion. But not all the dissolved electrolyte is dissociated at all concentration, and as the concentration is decreased, he suppose that the extent of dissociation will also increases, and there is a consequent increase in the number of ions. So this increase in the number of ions with the dilution is supposed to be responsible for the increase in molar conductance of a solution. So at infinite dilution, an electrolyte which is supposed to be the completely dissociated, and the extent of dissociation is often expressed in what? The degree of dissociation. It is simply what? How much ions are dissociated upon dilution. So it will be the ratio of ions which are diluted at particular concentration to the ions which are dissociated at infinite dilution. So the degree of dissociation of electrolyte is given the solution, and it is defined as the fraction of total number of moles for the dissolved electrolyte to that of into dissociated into its constituent ion. So according to the RNS theory, the molar conductance of a weak electrolyte is directly related to its degree of dissociation. So we can define this concept for the weak electrolyte, and based upon this degree of dissociation, we can be able to find out the molar conductance at infinite dilution. So at infinite dilution, an electrolyte is what? Completely dissociated, and its degree of dissociation is simply a unity. So we can say this alpha is equals to what? Lambda m upon lambda m naught. Okay, so this is lambda m is what? Molar conductance at particular concentration, and this lambda m naught is molar conductance at infinite dilution. So in order to find out the molar conductance at infinite dilution, there is another method which is called as a Collard's law of independent migrations of ions. So Collard's law of independent migrations of ions. So what he has done, he has just studied the various salts having the or various electrolyte having one common ion, and he has tried to like determine the uh, differences in their molar conductivities at infinite dilution. So he has proposed that uh, the common ion will not affect the overall conductance of or the molar conductance at infinite dilution. So based upon this, we can find out the molar conductance for individual ions. Okay. So what he actually done, that we can see here. So Collarge has made the study of various molar conductance at infinite dilution of a number of electrolyte using the an ion in common in it. Okay. So for an instance, the lambda m values for the sodium and potassium salts having an ion in common is x mine, and it is found that there is a constant difference. Okay, so here we can see this: if KCl and NaCl is used, the molar conductance due to chloride ion, and here also chloride ion will be same. So this difference is only due to the presence of potassium and sodium ion. So the constant difference between the molar conductance at infinite dilution due to the pair of this sodium and potassium salts having the same anion is seen to be the independent of nature of the anion that has been used. So here we can see this: here first KCl or Cl is used, here nitrate ion, here hydroxide ion are used. So even if we like change the anion, the difference is tends to be constant. Okay, difference is tends to be constant. So based upon this observation, so these Collarge has led to state that at infinite dilution, when all the forces of interaction between the ions has disappeared, each ion will migrate independently. Okay, so each ion will migrate independently of its co-ion, and it will make a definite contribution to the total molar conductance of a electrolyte. So we can say that each ion, so At infinite dilution, here you will see this, at infinite dilution this K plus as well as Cl minus ion will contribute independently of each other. So it will not be like depending upon K plus and Cl minus. So this K plus and Cl minus independently contribute to the overall conductance of a solution. So Colarge has put forward the law of independent migrations of ions by using the mathematical form, and it states that the values of molar conductance of an electrolyte at infinite dilution is equals to what, the sum of conductance of constituent ions at infinite dilution. So indirectly we can say this lambda m naught at infinite dilution is equals to lambda m naught of lambda plus of lambda naught of cation and lambda naught of anion. So molar conductance for the various ions, specific ions, can be obtained by using this method. Okay? And if you want to like find out the molar conductance at infinite dilution for acetic acid, how we can find out now that? So we have the value for acetate ion. How will you obtain this acetate ion? We can simply take the sodium acetate as a salt and we can measure its molar conductance at infinite dilution, and for acetate ion we will get certain value. Now for H plus ion also we are having certain values. So if you add these two values, that is for acetate ion and H plus ions, you will get the molar conductance at infinite dilution for the acetic acid. Okay. So for ammonium hydroxide, which is also a weak electrolyte, so for ammonium hydroxide also we can obtain the molar conductance at infinite dilution by using this Colarge law. Okay. So there are the few important application for this Colarge law. So we will try to see these applications one by one in the next lecture.